Thank you very much, Ethan, for the introduction. And thanks for joining our presentation today. I'm going to be providing updates on our research to refine copper-based treatments for zebra mussel control. I'm tag teaming with my colleague, Matthew Barbour, who is crunching the piles of data from this project. I also want to acknowledge our other colleagues here at UMass that have been instrumental in field and lab work, Matt, Todd, and Jeremy, and also Angelique Dahlberg, who has been a PhD candidate at the University of Minnesota, advised by Nick Phelps. Angelique has presented her portion of this project in past years at the showcase and is now finishing up her degree. I am going to turn off my video just for the remaining part here because of connectivity issues. So I apologize for that. So there are over 200 lakes in Minnesota that are listed as infested with zebra mussels, and that number has been increasing every year. So the problem with zebra mussels may not always be obvious to people that are recreating or living on an infested lake. We often hear people say that the water is clear in their lakes after zebra mussels, but what that really means is that they've reduced available food for other native plankton feeders and changed the lake ecosystem. They also degrade beaches and shorelines and foul structures in the water like docks and even boat motors. The options for controlling mussels are somewhat limited, but one tool that has been used as a pesticide is copper-based products. They've been used to combat nuisance aquatic species such as plants, algae, and snails. Copper-based molluscicides have been used in Minnesota to manage zebra mussels since 2011. So our research has been focusing on how those copper treatments can be refined to reduce the cost and the non-target effects of copper. Our presentation today includes an update on phase 1 of this work, which we started with the bay-wide low-dose copper treatment in 2019, and then followed that with 3 years of post-treatment monitoring. Next, we'll provide an update on phase 2 of this work, which was another bay-wide low-dose copper application in 2022, with some modifications based on what we learned from phase 1 and from some laboratory work. Matt will also present preliminary results of a study that we've just recently are finishing up to compare the seasonal sensitivity of adult mussels to copper. And then we'll finish with an overview of a planned structured decision-making workshop with stakeholders in 2024. Invasive species management is oftentimes approached from an all or nothing standpoint. If we can't eradicate them, we just have to live with them kind of perspective. So numerical eradication or complete extirpation might be appropriate for new infestations that are small in size and geographic area that can be isolated. But for established populations in a large water body, a whole lake, for instance, eradication might not be achievable, especially when there are concerns about what effects that treatment could have on native species. So functional eradication aims to reduce a population below levels that can cause negative impacts and then maintain the population below that level. And this is a strategy that has been used successfully for management of other invasive species like rusty crayfish, green crabs, and red lionfish. So this project is evaluating a functional eradication approach to zebra mussel management, specifically to reduce the populations by reducing recruitment. So as part of this approach, we aim to minimize non-target effects by using less copper. And that meant that the treatment had to target the most sensitive stage in the life cycle, which is the larvae or the veliger. So after adult spawn, the veliger develops in the water column over several weeks before settling to the bottom. So this is the stage we're targeting with these low dose copper treatments. The product we've been testing is EarthTec QZ, so it's about 5% copper. It is a registered molluscicide, and the label allows a maximum of 1 part per million of copper applied to 50% of a water body. So this is the product we're testing, but this is not an endorsement of it. The first phase of this project started in 2019, and you've probably heard past presentations on those results. It occurred in Lake Minnetonka, where St. Albans Bay was treated with EarthTec. That's the lower pink area on the map. And Robinson's Bay was the reference, which was the upper pink area. So copper was applied to the upper water column or the epilymnium every other day for 10 days at a mean concentration of 80 parts per billion. So just keep in mind that's 8% of what's allowed by the label. We then monitored St. Albans Bay and Robinson's for 2 years and St. Albans for an additional 3rd year to determine how long the mussel population was suppressed after treatment and how the native communities responded. So we have previously presented the results from 2019 to 21. So what's new this year are the 2022 results. And today I'm just going to focus on 2 main highlights, that is zebra mussel settlement and response of the most sensitive non-target group, which is zooplankton. So the graph on the left shows the number of veligers per liter, and on the right is the number of juvenile mussels that occurred on settlement plates, which we measured those in both August and October of each year. So the treatment bay points are shown in black and the control bay in red. The dotted vertical line there is indicating when the treatment occurred. So you can see that the low dose treatment effectively reduced veliger density in 2019, 20, and even into 21, it was relatively low. This resulted in very little settlement on plates in 2019 and 2020, but we saw then in 2021 that settlement increased back up, similar to what we had in the control bay or Robinson's Bay. And that increase continued into 2022. So now we're looking at both veliger abundance and settlement in 22 that were similar to what we had either pre-treatment or in Robinson's Bay. So overall, it looks like the treatment successfully reduced settlement in the first 2 reproductive seasons, but to sustain the reduction, follow-up action would be needed. We also monitored benthic invertebrates and the zooplankton community. I'm only showing results of zooplankton because they are the more sensitive group to the copper. So on the left, we're seeing zooplankton abundance. Again, the treatment points are shown in black and the control bay points in red, and that vertical line is when the treatment occurred. So we had 1 sampling point before the treatment, and you can see immediately after, this was 1 day after the last treatment, zooplankton abundance did drop. It started to go back up again at 14 days after the treatment. However, in phase 1, we didn't sample the zooplankton after 14 days until the following year. So in 2020 and 21, and now added to that in 2022, we saw that zooplankton abundance did recover in those subsequent years after the treatment. So there was no long-term suppression in the abundance of zooplankton. We also looked at changes in the community composition over time to see if certain groups were more sensitive. This graph on the right is non-metric multidimensional scaling. It's a way to show similarities in a multi-species community. So this is showing that composition in St. Albans, the greater the distance between 2 circles, the more different the communities are at those time points. So the most obvious separation is between the pre-treatment composition, which is shown in the red circles, and 1 day right after the last treatment. Those are shown The gold circles with, or the gold area with the gold triangles. So the treatment very definitely did change the zooplankton community immediately after the treatment. And from this, we also found that the group that was most sensitive was cladocerans, which are things like Daphnia or water fleas. However, you see at 14 days that composition starts to creep somewhat back over closer to the pre-treatment composition. So again, an indication that there was some recovery. And at 1 and 2 years, that's the green and purple and pink clusters there, very similar to pre-treatment. So again, it shows that there was recovery and not a long-term effect on community composition. But as I mentioned, a piece that was missing here in this monitoring was what happened between 14 days after treatment and all the way to the next year. So you'll see that we added that to phase 2 of this project. So phase 1 of the research showed some success with the low dose copper strategy, but we still had a lot of questions. Was it repeatable in a different bay that was larger in size, and could we use less copper? So phase 2 of the research started in 2021. It differs from the first in several ways. We again selected 2 bays in Lake Minnetonka. This is North Arm and Maxwell. They both have well-established zebra mussel populations. Maxwell was selected for treatment. It's 125 hectares, so it's twice the size of St. Albans. We also identified areas within each bay that were more similar in substrate and vegetation. So they provided a better comparison for us of treatment effects. And based on lab work in 2021, we lowered the target copper concentration from 80 to 45 to 50 parts per billion. The application in St. Albans was to the whole bay, but shoreline treatments are more common in EarthTec applications in order to limit it to 50% of a water body. So this is the approach that we used in Maxwell Bay also. So we conducted pre-treatment sampling in 2021 to establish baseline information on native communities and zebra mussel density, and then expanded our monitoring to include phytoplankton communities and also increase the frequency of our sampling of those non-target communities. And now I'm going to turn it over to Matt to present updates on the phase 2 results.
Well, so just to recap the actual copper application that took place between July 20th and August 1st on 2022, you can see that our pre-treatment monitoring of copper shows very minimal background copper detected. In fact, a lot of it was below detection of our instrumentation, which is fairly sensitive. And then you can see the very clear spike during our treatment window, highlighted by the arrows in the bottom. And then copper concentrations in the water column kind of dissipate over time. It's important to know that this copper isn't necessarily leaving the environment. It's actually just being bound by what we call ligands. So organic complexes that are present in things like the sediment, which will bind the copper, and it tends to be more or less sequestered in that fashion. It takes a lot to get that copper cleave back on and kind of reanimated within the system. We did notice a similar trend with the veliger density. Again, you can see the kind of seasonal trends with a increased production as the year progresses into the summer with warmer water temperatures in both bays. In 2021, you can see kind of an unaffected pre-treatment baseline of that phenomenon. In our treatment year, the treatment is beginning is marked with that dashed line, and you can see that we've greatly disrupted that trend, and it appears to have successfully sequestered or eliminated many veligers from the water column. Again, similar to St. Albans Bay, this is also reflected in settlement. We did just get our final samples for this year back to the lab, so there will be a 2023 extension to this graph as well. But we haven't gotten through all that data yet. I haven't even gotten a chance to count the mussels yet. But here we can see that suppression of veligers panning out into suppression of settlement, even into the following year. And just for some kind of qualitative observations on what we've collected so far this year, there is some settlement that is occurring in Maxwell Bay. Strictly qualitative observation, those mussels appear to be quite smaller in size. We're not sure if that's necessarily a treatment effect or if it's a habitat effect, but either way, there's a higher degree of variation we're seeing given the size of the bay. So with the zooplankton, here you can see far more points on these graphs in following up on our more increased sampling intensity. We did see a very similar response in the zooplankton community. That is decreased abundance of native zooplankters on the top of the graph here. You can see the dotted line representing the treatment again, that immediately following the treatment, zooplankton numbers were down. This also had an effect on diversity with changes to more sensitive species being more absent after a copper treatment. There's a decrease in diversity immediately following the treatment. The nice thing and the reassuring thing here that we capture, unlike St. Albans Bay, is that in a little over a month following the treatment, we see those numbers rebound to pre-treatment and even arguably increased diversity compared to pre-treatment conditions. So that's a pretty promising result. Adult zebra mussels in St. Albans Bay and likewise in Maxwell Bay, we noticed a increased mortality in adult zebra mussels at these concentrations. The data that we have on hand for copper toxicity to adult zebra mussels predicted a far less mortality in adult zebra mussels given the copper concentration. So the amount of adult mortality was a bit surprising and higher than we would have guessed with in regard to zebra mussels. Our native mussels held up fairly well with 75% or more survival come 30 days after the treatment. The graph on the right, we measured shell length as a function of growth. We did notice a statistical difference in these growth rates as represented with the lines and the shaded regions for confidence intervals. However, given the individual measurements at each time point, there's not really a difference between each time point, but a difference in trend. And we're not sure if this would actually be more suited for a nonlinear type model, as growth is rarely linear. The other thing we did monitor with the native mussels is glycogen as a measure of health. There was no significant difference in glycogen concentrations between the two bays, which is an important note. So just to kind of go over, we did reduce settlement within the treatment year. A year later, it starts to become more similar. So there's the zebra mussel population seems to be rebounding a little faster than did in St. Albans Bay, but there was a high degree of variation within the bay. Zebra mussels, adult zebra mussels were more sensitive to the copper treatment and even more sensitive than our models predicted. Native mussels, there was some slight reduction in growth rate, but we think that if there's mussels there, they're probably still doing okay. Zooplankton followed very similar trends to those observed in St. Albans Bay. This time, though, with extended monitoring within the treatment year, we were able to see some recovery and arguably even better diversity in the native population than we did before the treatment. So we're still awaiting our phytoplankton community analysis in the benthic invertebrate community responses, as well as all of the settlement and stuff that we literally just got back to the lab yesterday. So still very much crunching numbers and just trying to get the numbers in the first place. So more to come on that. So with the increased susceptibility to copper exposure that we witnessed in both St. Albans Bay and Maxwell Bay, it had us thinking that there is likely a seasonal trend to copper sensitivity in adult zebra mussels. So we began collecting zebra mussels back in early June, coinciding with our collection trips to Lake Minnetonka. We collected all the mussels from the same bay, Robinson's Bay, so it hadn't been treated by us with copper at all anyway. And we selected a size range roughly between 15 millimeters and 20 millimeters and decided to expose them at within 2 days of collection and at the temperature at which we collected them, so that we can maintain as much real world application as possible instead of introducing laboratory variables that could influence toxicity. We followed a standardized toxicity testing format and collected mussels every 2 to 3 weeks. We are just kicking off the 7th and final trial tomorrow. So this is partway done and very preliminary in nature. We did notice out of the groups that we collected that there are differences throughout the year in mussel condition, represented with the graph on the right. As the year progresses, there seems to be a decline in condition. We think that this is highly correlated with reproduction. So as the mussels are releasing their gametes, it reflects in their dry tissue mass and thus kind of skews these numbers a little bit, which is all represented in previous studies from other facilities as well. So it's kind of nice when everything lines up across different laboratories. We did notice quite a significant shift in copper sensitivity. Our first 2 trials, we tried to induce a spawning event with serotonin in the laboratory to see if it's stresses of spawning versus strictly seasonal stresses. As you can see on the graph on the right, the T1 and T1S trials. The S stands for serotonin, so that's the same lot of zebra mussels. It's just one was exposed to serotonin the day before a trial to try to induce spawn. No real significant differences between those two, so we did not pursue the serotonin exposure anymore at that point. An important thing to notice, though, is that the concentrations that we exposed at, we were not able to accurately model in LC90, so those 2 values are extrapolated on the table on the left-hand side of your screen. The red line on the graph on the right, though, is roughly around where the LC50 would be for comparative needs. So in early June, we were looking at LC50s of around 400 and greater micrograms per liter, and that shifted as the season progressed. So come late August and even late July, around the times when our treatments were occurring, LC90s were considerably decreased, as were the LC50s. And if we were, I'm not sure if my cursor shows up at all, but if you were to imagine a number 30 down here on the bottom, so around the 30, a 30 on the left-hand side of your screen, and where that coincides with concentration. So 30% mortality lines up with right around the concentrations that we're treating at. So this kind of reassures us that there's a temperature-related phenomenon occurring with mussel susceptibility, which is a large consideration for resource managers to consider, particularly with early detection rapid response treatments that could happen at various times throughout a year, just to take note on, how sensitive mussels may be in the time of year. So we're going to continue to crunch numbers on this. We also took a suite of physiological markers and enzyme assays to try to see if there's alterations in muscle condition and physiological function, and try to tease out some more information to be more informative. So our low-dose copper treatment is clearly not an eradication attempt. We're trying to reduce a AIS species population below a certain threshold, which may free up resources, decrease competition, and allow native species to thrive. This idea from Green and Grauschultz needs a lot of information to feed into it. What we do have a very good grasp on is the population density driven impacts of zebra mussels as they are establishing a population. What we don't know is how an ecosystem responds when we reduce their population below wherever that critical threshold may be, and where is that threshold? These are the big questions that we don't know yet. What we do think, though, is that even with a removal or a suppression, there's actually two disturbances in place. There's disturbances from the treatment itself, so think non-target impacts, as well as the removal of a high impact species that is considered an ecosystem engineer. They greatly altered the ecosystem functioning with their introduction and establishment. How does that impact the ecosystem just not having them there? These are all big questions that we don't know. So the tail end of these curves, we don't know what the fallout is, and there's really only one way to get to that point, and that's through experimentation like we've been doing. There is an added benefit to looking at suppression, and that's through a containment mindset. By targeting source populations, propagular source populations of zebra mussels from key lakes, it's possible to reduce propagular pressures on uninvaded areas. So considering this at more of a regional level for containment may also be suitable for resource managers as well. But that takes into account other things that people from MACERC have been working on as far as vector routes and population sources and so forth like that. So there's a lot of things to consider with this as well. And when considering something like functional eradication or containment via suppression, it is completely objective dependent. There is not really a one-size-fits-all approach to these problems, and what one lake management system may want is completely different from a different lake. So these are all things to consider, and I'll turn it back over to Diane to start pondering how we get to those decisions.
Yeah, thank you, Matt. So really the culmination of all this work that we've been doing with low-dose copper, along with drawing in information and data from other open water control actions, will be a structured decision-making workshop in 2024. So structured decision-making is an opportunity to bring the science together, but also to bring the stakeholders in to establish management goals for invasive mussels. So we may be asking the question, how can zebra mussels be managed in Minnesota lakes? Is that eradication? Is it suppression? Or is it to live with them? And so if the action is a goal, the workshop is also a way that we can identify those high value kind of priority habitats or lakes for where those actions will occur, and evaluate what tools are most suitable for it. So we can start with kind of a general approach, but as Matt mentioned, it would also become kind of lake specific. So with that, Matt, if you want to go to the next slide, I want to make sure that we thank all of our funders and supporters funding for the project provided by the Minnesota Environment and Natural Resources Trust Fund through MACERC and the Minnesota Legislature, Hennepin County, Pelican Lakes Association, the Fletcher Family Foundation, Bay Lake Improvement, USGS, and Environmental Protection Agency. And we also got a huge amount of support from the those listed on the right. We could not have done this work without support of local people, especially around Lake Minnetonka. And so the last slide is just, we'll open it up for questions.
The first one comes from April. She says, "Thank you for the updated data. Very promising management strategy. The question is, if not all of the copper is getting taken up by the zebra mussels, about what percentage then gets bound up by the environment? And does that have long-term impacts?"
Yeah, so we have been measuring water concentrations of copper at all of those sampling points that you saw, as well as taking samples from the sediment. So we have an idea of how much of it is bound by the sediment. A lot of copper does end up in the sediment or being taken up by aquatic vegetation, and I don't know that we can completely answer that question. What we're also finding is that there's other copper treatments occurring. So the copper that we're measuring is not just what we've put in the water.
Yeah, right before you mentioned it, it came into my mind. We totally forgot to mention that we are sampling sediment for copper at all of our sampling locations in Maxwell Bay and North Arm. And we are detecting even Robinson's Bay, where we have not done any copper applications whatsoever. We're still, even this year, with the collection of our zebra mussels, measuring copper in that bay. So we think that there's either illegal applications taking place or something happening where there's a copper source. To expand on the where the environmental faded copper, I'd argue that the bulk of the copper that we add ends up in sequestered within the environment. Even the copper taken up by mussels, when the mussel dies and degrades, that copper is still there. It's not like used up metabolically or anything. So it's going to be a legacy chemical. Even from the early 1900s, there's copper being found in sediments around Madison Lakes in Madison, Wisconsin, from vegetation treatments that occurred there in early 1900s. So,
few minutes left. Regarding seasonal copper toxicity, has any consideration been given to conducting similar lab tests with other species such as small fish, zooplankton, macroinverts?
Yeah, we haven't done that. The focus of this seasonal study was really to see if we could optimize mussel mortality by understanding when the adults were most sensitive. Because as Matt mentioned, we have in both phase 1 and phase 2 in both St. Albans and Maxwell, we monitored adult mortality as a result of the treatment and did see greater adult mortality than what we would have predicted. And so there has been some question about whether their adults would be more sensitive right before they spawn, during spawning, or after. So this part of the study was really aimed at trying to answer that. When would be the optimal time for the treatment to kill both veligers and as many adults as possible? So no, the short answer is we have not included these other non-targets in that testing, but it certainly would be worthwhile.
one of the nice things about working with copper too is there is a good deal of copper tox aquatic toxicology papers out there on copper and its effect to various life stages and various species across the board. So there's a lot of existing data to look at. Seasonality within that data, though, I don't know if it's actually like reported when, but perhaps more importantly is like life stage, especially with dealing with zooplankton, because they're not strictly like a calendar year like we see with zebra mussels, where there's a true spawning event and then they kind of go dormant. They're constantly changing, constantly reproducing. It's a pretty fast turnaround, which is why I think we see the fast response back out of them. Daphne will start reproducing in, what is it, like 14 days, I think, Diane, something like that, 21 days.
Yes.
I mean, their life, their generational turnover is much faster, and that's why we're seeing a faster response from them, is what we think, at least.
This next question says, it seems like the treatment effects wane after 2 years, so it would seem that treatments would be needed every 3 years to get long-term value. Does this seem accurate?
For this, I think that does appear to be true in St. Albans. I don't know that we could apply that across the board to every lake. And I know it's a different system, but they've done control actions in Lake Erie, and the gobies are actually sustaining that treatment by eating any young zebra mussels that might settle. So I think that it is something that we'd like to investigate. What would make the treatments kind of maintain that depression in the population for a longer period of time?
Which is not an endorsement to introduce gobies into your system.
No, definitely not. Definitely not. Or any other
Yeah.
invasive fish. No, we don't want to solve one invasive problem by introducing another.
So the strategy absolutely is going to need more refinement and more understanding at application intervals. The best way I've been able to wrap my head around this functional eradication paradigm when I first started reading about it was to think about a farmer, because it really is just a pest management strategy. So a farmer, when he applies a pesticide, his goal is not to eradicate the weevil. He's going out at a very targeted time with a very targeted product and very clear objectives in mind, and making his application so that his objectives, which would be increased crop yield, are met. So putting it in kind of a mindset like that, the strategy really makes sense. We just need to know more about the various populations that we're dealing with and targeting, and then having a very clear objective in mind when doing so.
The next question says, how many species of native mollusks were monitored?
Zebra mussels have really highly impacted the native mussel population in Lake Minnetonka. I guess the species most common in there is the fat mucket, or Lampsula silicoidea. And so that we actually propagated the juveniles, so because there aren't really many to find anymore in Lake Minnetonka. So we propagated them here at the facility and then use those juveniles in the study. So it was just one species. And I think the species diversity in the lake is, I don't know what it was historically. I know like 5 years ago, we could find maybe 2 species, and we really had a hard time finding any at all for this project.
This one says, what are the alternatives to copper-based mollusks? I probably said that wrong, for controlling zebra mussels.
So as far as registered products, molluscicides, there is EarthTec QZ and then Zequinox, which is a biopesticide. And right now, Zequinox is kind of cost prohibitive. It has been used once in a while, but just because of the cost and application problems, it's not used as routinely as EarthTec is. Short of that, there's, for localized control, there's things like benthic mats. We are also have been investigating the use of carbon dioxide which if you can maintain the concentration in an area, will prevent settlement and also kill the adults at a higher level. Other than that, you know, there's physical removal, which is also very labor intensive and would only be used in a very limited areas.
There's also the example of Millbrook Quarry out in Virginia with the
Yes,
potassium chloride, but that was a very specialized permit. And they treated it so hot that they're still detecting pretty significant amounts of potassium in the water column. But their objectives there were to eradicate, because they use the quarry not as a fish production area at all. It's to train scuba divers. So again, objective based.
yeah.
Yeah.
The potassium chloride or potash is not registered, but it has been used several times just with an exemption.
Yeah. Christmas Lake right across the street is another example too. Right across the street from Lake Minnetonka, I should say.
Yes.
We have one final question here. Is it safe to swim in the water after application of EarthTec QZ or other copper molluscicides?
Yes, the EarthTec QZ label does not have any re-entry restrictions. It is considered safe to swim in.
Yeah. If I recall to the 1 part per million label, I think that's safe enough too for drinking water by EPA standard, if I recall. So
Yes.
would I personally go water skiing right behind the application boat? Probably not, but I mean, it dissipates and spreads pretty fast. So there's no real concern.
Okay, thank you so much. Join me in thanking the presenters today for sharing this research.